Okay, hi. So we are in week 5 now, and the first thing that we are going to do in week 5 is that we are going to have a look at certain operations that are there in arrays. Okay, there are two most common operations, searching and sorting, but there are two fundamental operations as well, which are insertions and deletions. So basically, this is what we are going to have a look at in this particular lecture. But before that, let's have a recap of what we already know about arrays. So arrays, as all of you might already know, they are just collections of variables of the same type. This is important that they are of the same type. We'll see what collections of different types of variables are called, but that will be in later weeks. And individual variables can be accessed with the help of an index. So this index starts from 0 and moves uh, up to size -1, and the size of an array remains fixed. Once you create it, there is just no way you can change it. You can neither shrink it nor expand it. And so we have also seen certain ways in which these elements can be initialized. um, Usually we make use of loops. Okay, so till now, before we had studied loops, we were trying to access these indices directly, but maybe in the previous week we already have seen that it's always the best to use a loop to iterate through these indices and do whatever you want with them. And as I said, in this lecture, we are going to have a look at two very important operations that people usually perform over an array. This is basically to look for a particular value in the array called searching, and sorting the values inside the array. Sorting essentially means you're just trying to put them in some kind of order, okay, increasing or decreasing order. So let's just start with a non computer science example. So I'm not sure how many of you have played these card games, but in these card games, usually these cards are numbered, right? So in a typical card game, you have these uh, twos, threes, fours, and then they go up to 10, and then you have a J and a Q and a K, right? I mean, and then an A, right? So there's some order in which these cards are there. So the players of these card games, normally what they do is they try to keep whatever cards they have got in a particular deal in some kind of an array, or in some kind of an order, right? So basically it could be the increasing order or the decreasing order. So they just want to keep their cards in some particular order. It just makes your game playing more efficient. But when they actually get these cards, right, so there is some kind of a randomization involved, and when they get these cards, they are not really in any kind of order, right? So it looks something like this, right? So there is really no order here. So what, how do these card players sort their set of cards? Well, there is one very common approach that you may not use this approach, but this is a very common approach. Especially this is one that I use. So what I do is I browse through all the cards, and I just pick up the smallest card that is there. Throughout all my cards, I just find out the smallest card. So let's just say in this case, it will be the card with number 2. Again, I mean, this is a very crude example, so I'm not really caring about the type of the card, right? So just assume that uh, you know we're just trying to we just have cards of the same color. Okay, so they're all heart cards. Anyhow, so basically this is the smallest card and that I have in my hand. So I just pick it up, and what I'll do is I'll just bring it out on the top, so something like this. So I picked it up from the middle, and now I have brought it on top. Now now whatever cards I have left, I just try to do the same again. So I'll find the smallest card among them. So let's just say in this deck now the smallest card is 5. And then what I do is I just place it right next to the card that I have already placed on the top. So basically I just place it next to 2. This is what I'll do. And if I just keep on repeating this process, finding the smallest card, and then keep on adding them one after the other, uh, in this way what I'll really have is that my cards will be sorted. Okay, sorted as in they'll now have a particular order. It could be, smallest to largest or largest to smallest. Depends on how I would like to keep my cards in my hand. um, Now, assuming that these set of cards, right, whatever you just saw, they were basically numbers, right? Each card had a number. So if you just assume that each of these cards represent a value inside an array, and this whole set of cards represent an array, what we really did just now was that we should reshuffle the values of an array, and we've ended up putting them in some kind of an order, okay, right, as an increasing or decreasing order. Also, what we were just doing, right, we were just taking out a particular card from the array, and then we were putting it at some other point. We were inserting it at some other point. So essentially, we used two very basic operations that we do on array: insertions and deletions. We were essentially deleting a card first from wherever it was, and then we were inserting it at some other position, the correct position, to be honest. So let's just see what insertions are. So again, insertions and deletions are not really specific for sorting purposes, right? I mean, these are two general operations that people do on arrays. So let's just have a look at what insertions are. In this card sorting example, what we were doing was, after finding the smallest card, we were simply inserting it at its appropriate location. So now, here we don't really care what, how that location is found. Insertion is all about inserting something at a particular index, right? What exactly is that index? How exactly are we coming to that index? That is not necessary. That is not a part of the insertion logic. The insertion logic is all about, figuring out a particular slot where a particular value has to be inserted. So how does insertion takes place? So essentially, the first thing that we do is we check if the array has any place for accommodating more elements, right? So now this is something that we may have not discussed before, but many a times we'll actually declare arrays which are sufficiently large, even though we don't really need to store those many elements. In fact, some of you might have already done that with strings, right? So you might have created strings of much larger sizes than what you were actually going to use. So the first thing that we need in any kind of insertion operation is that we need that the array should have some space, okay, where a new element can be inserted. So this is the first step in the insertion, that you actually check if my array can accommodate more values or not. Then the next thing I do is I have to provide a particular index, right? So the new value that I want to be inserted inside the array has to go at a particular index. So let us just consider that index to be I. So then what I do is, essentially what I have to do is all the elements that are currently at index I, as well as those which are on the right side of I, right? So basically indices that are greater than I, they have to be shifted, right? So it's like, I have to create some space, okay? I have to create one element space. And how do I create the space? I basically push everything to the right so that a space gets created, and then finally, when the space has been created, I just put the new value at that particular position, at that particular index called I. So this is a very simple example. Let us just say, I have this array. uh, Again, now I am going to use two different terms here. I am going to use the term capacity and the term size. Now, capacity is just basically, whatever we have whatever we have have called size till now. That is basically capacity now. But so capacity is basically the size with which you create the array. So that is capacity. Now, what exactly is size? So size is essentially the number of elements that you are storing in the array at any particular point, right? So it is possible that your array might not actually be using all the space it has, right? So this is particularly true for strings. For example, in the cases of string, you might actually uh, have more space inside your array as compared to the number of characters that you're storing there. So basically in this particular example, I have my capacity as 5 and my current size is 4. Okay, so it doesn't it so essentially what I'm trying to say is that this last element here, uh, I just don't care what it is. It is not necessary that uh, I essentially deleted this. So deletion essentially means that I simply don't care what. So x means don't care. Okay, it could be any random value. It's just that I don't care about it. So now what happens is I get an insertion request. Insertion request as in it says kindly insert the value 20 at index 1. So again the indices are something like this: 0, 1, 2, 3, and 4, as I saw in the as I showed to you in the last slide. And now I have to insert this value 20 in this one. So the first thing I do is I just check whether the first thing I do is just that I check whether this particular array has any capacity left. So I just say, are there any vacant slots? Yes. Why? Because the capacity is 5 and the current size is 4. So I do have one slot left. Okay. Of course, that slot is lying at the end of the array. So what I do is I start this shifting process. So what happens in the shifting process, I just keep on shifting these elements to the right. So I have to insert it here, and I have, as I said, I have to push these values to the right. So what I do is I start pushing them. So the first thing I do is I push this 5 to this location. So now 5 comes here. Then I push this 9 to where 5 was. So now 9 comes here, and then I push 13 to where 9 was. So now now these values have basically been shifted by 1. You can see, starting from here I've reached here, and then finally I can put my 20 at this particular location, right? So this is the very simple example of insertion. And now I don't have any more vacant slots because my size has equaled my capacity. So one of the things that you have to understand is that now I'm explicitly maintaining another variable, okay, and that is the size of the array. So whatever we have done till now, we were basically not differentiating between capacity and size, but essentially this is something. There is a new term that I'm simply introducing. I'm saying capacity is the maximum number of variables a particular array can hold, and a size is the actual number of variables it is holding at actual number of values actually that it is holding at any point of time. So the size of an array can now range from 0 to its capacity, and as I say, array capacity is essentially its declared size. So when you are declaring the array, you are just giving that number, right, in square brackets. That is now basically your capacity. So this is just some C code. I'm not going to go through the whole C code. This is there in the examples that I share with you. It's your responsibility to go and read it. But essentially, what I'm just trying to show here is that insertion requires two operands. Okay, so the first operand that I'm taking here is basically the index at which you want to do the insertion, and the second operand is the value that has to be inserted in that particular point. So there are two operands when you do insertions, and this is the actual code, the actual C code which is doing the insertion. It is your responsibility to read it and understand if this works or not. Now, similar to insertion, there's another operation called deletion. So what we were doing in that card sorting example was that we were first deleting an element from the array, and this was essentially creating a space. Okay, right? Because again, it's very abstract, but the idea was that if I had 5 cards in my hand and this was corresponding to a 5 element array, as soon as I picked up one card out of those 5, I just reduced the size to 4, and now I have one vacant space in the array, and now I can insert it at some other point. So essentially there were two operations that I was doing. I was starting with a deletion, and then I was doing an insertion. So now deletion is a more simpler operation than insertion. So deletion simply involves checking the array if it actually has any elements, right? So you cannot delete an array that is already empty. So you first check if the array has any elements. then you tell me, okay, I want to delete the element which is at this particular index. Again, let's assume that this index is I, and then what we do in deletion is that we actually shift the elements that are there, right? In insertion, I actually push the elements to the right because I have to create additional space, and in deletion I push the elements to the left because a new vacant space has come up in my array. And if you remember, I was just keeping my vacant spaces towards the end of the array. So the idea is that now you have to push the vacant space to the end of the array, which essentially means shifting the elements to the left side of the array. So, to fill up that void that will be created when you delete the element. So again, just assume that the same array in which we added 20, right? So we added 20 at the index 1. So now let's assume that I get an inverse operation of that insertion. So now I'm going to delete that element 20 that I simply added. So now what I'm going to do is, in insertion I was pushing values to the right. Now I'm going to push values to the left. So what I'll do is I'll simply start from 13. I'll just copy 13 back to one step on the left. Then I copy 9 again to one step at the left. Then one more, copying one more shift from right to left. And now essentially this particular plot, okay, that is what I was saying, that this is just essentially don't care. Even though the value 5 is there, I simply don't consider it because I have decreased the value of size, okay, from 5 to 4. So for me, my array simply ends here, and I really don't care whatever is there, right? So this is the whole idea of deletion, and this is the parallel, code. Just like insertion, I now have a parallel code for deletion. Parallel, as in, this is the corresponding code for deletion. Now what you can see here is that deletion only needs one operand, right? I just need the index. In insertion I needed two operands, the index as well as the value to insert. Deletion just needs one operand, and you simply say this is the index at which I want to the value at this particular index must be deleted, and this is the corresponding code which deletes the element. Again, it's your responsibility to read and understand how this works. Now there is, we actually started with a sorting example, but we took a digression to actually cover two common array operations, insertions and deletions. But let's just go back to that same sorting thing that we were doing. So what we actually saw in that card sorting example was a variant of a very popular sorting algorithm called the insertion sort. Okay, and we use insertions and deletions in a more systematic fashion when we are doing insertion sort. So the idea behind insertion sort can be summarized something like this. At each step what we really do is that we divide the array into two imaginary parts. So remember, these are imaginary fluid parts, okay? They are not really it's not like we are creating two different arrays, okay? Basically we're just having some markers. So it's like putting a bookmark in your book, and as soon as you open your book is basically divided into two parts, right? The part on the left of your bookmark, and the part that is on the right of your bookmark. So similarly, we are just having a kind of a marker in this array, and I simply say that now I have divided my array into two parts. One part of this array, which is usually the left part of the array, we simply say that this part is always sorted, okay? And while the other part, the right part, is unsorted, so that has still we still have to sort that part. Now when we start, what we simply do is we just put the bookmark after the first element. Why? Because the first one element array is sorted by default, right? There is no need to sort a one element array. So basically, if I put the marker in the beginning, right after the first element, I can say that the left part is sorted and the right part is unsorted. Then the unsorted part becomes, it has size minus one element. The sorted part has just one element, and the unsorted part has size minus one elements. And then at each step, what I do is, I pick the first element from the unsorted part, and I simply insert it at its correct index in the sorted array. So in the card sorting example, I was not picking the first card. Okay, that was another way to do it, but I was basically finding the smallest card and then putting it in the right place. Here I'm just doing it in a more systematic fashion. I simply pick the first card in the unsorted cards, and then I put it at the right place in the sorted set of cards. So you know what happens it at each step, the sorted part of the array increases by 1. Why? Because now I have two elements which are in order after the first iteration. After the second iteration, I have three elements which are in order. And if I keep on doing this, okay, I'll keep on decreasing the size of the unsorted part. And when the size of this unsorted part becomes 0, the whole array has become sorted. So let's see a simple example. It is the same array that we have been looking for now. Um, so so in the beginning, what I'm saying is, I'm just putting my marker at this point. Okay, this is my markers point. So left of my marker, everything is sorted because it's a single element, so it is sorted by default. And right part of my marker, it's the unsorted part of my array. So that is simple. Now uh, what I now do is, I basically delete, again, this is all happening in an imaginary fashion. We are not really deleting it. It's just like a imaginary way. We have to think like this. So we delete the first element of my um, unsorted array, and that is what, that is 20. And then what I do is, I try to put it inside the sorted part of my array. So this is my sorted part of the array. I just have to find exactly where in the sorted part does this 20 go. And then I realize, okay, 20 already has, it must come after 10. So the size of my sorted array has increased by 1. 20 has come here. Again, I didn't really do anything here because 10 and 20 are already in order. But if we had an element like, let us say, 7, right? So then I would have put 7 here, and 10 would have been here, right? So as 7 would have been inserted at index 0. But because 20 is already larger than 10, 20 is basically inserted at location 1 right after 10. So I have really not done anything, but we have completed one iteration of insertion sort. So in the next iteration, now the unsorted array has become a slightly smaller, and 13 is the first element of the unsorted array. I pick it up, and then I try to insert it at the correct location. So now you can see that I have to shift 20 to the right, because the 13 has to be inserted at index 1. So I had to shift 20 to the right. And again, you can see that the sizes of this sorted and unsorted part, they are fluid, right? Fluid as in, they are basically imaginary parts. They are not really rigid arrays. Otherwise, in a rigid array, sizes do not change. But here I'm just saying that they are imaginary arrays. They are part of the same array, so I can freely shrink or expand either of the two. And this is what I'm doing at each step. I'm basically shrinking the unsorted array, and I'm expanding the sorted array. Okay, so I picked up 13 from there, and now it is there. Now in the unsorted part, the next element is 9. So I simply delete it from there, and in the next iteration, I find out where it should be inserted. It should be inserted at index 0. So now all these three elements have to be shifted to the right. It's an insertion. So, and the 9 is to be inserted at this particular location. This is now one more iteration of my insertion sort. My sorted array has expanded. My unsorted array has shrunk again. Now this is the last point. At this point, I simply delete this 5 from the from the unsorted part and then put it in the sorted part at this particular location. Again, this also involves shifting of all the elements like this. So now, at this point of time, our unsorted array has become, the size of the unsorted part of the array has become 0, and we can declare that the array is sorted. So what you just saw is an example of insertion sort. Now there's one more operation that I have to talk about, and that is searching in an array. Now you guys have already done that, I think, in the assignments uh, and probably uh, all the practice code that you've been writing. So how do you actually search for a particular element in an array? So till now we didn't really have much of an option. We just had to go through all the indices in the array one by one and check if that particular element is present there or not. So by the way, this is also known as linear search. Okay, you have to linearly go through the array and find and check for each and every instance, each and every variable. But let us say you have a sorted array. You can actually make it a little more efficient, and this is why sorting is so important. If you have a sorted array, the searching time within the array can be drastically reduced. How? So let's just see. So assume that you want to check for a particular value in the array. So you pick up a random index. Okay, let us just call it I. Okay, so the I, your indices range from 0 to size minus 1, and you have picked some value of I. And now what you do is you basically check what is the element at this particular index, and if this is the element that you were looking for, you've hit the jackpot. So you have searched the element successfully. But even if that element is not really what you were looking for, you still have a hint, right? What is that hint? You have actually again divided the array into two parts, and this is a very common thing that we do in problem solving. Whenever we are trying to solve a problem using arrays, we just try to make it smaller, right? At each step, I'll try to make my problem slightly smaller than the problem at the previous stage. So this is what was happening in the sorting example as well. At each step, I was just reducing the size of the unsorted part by one, right? And then if I keep on reducing the size like this, at one point of time, the whole array will be sorted. Now similarly, what is happening here, when I actually check my element with the element at index I, I can now essentially say that my array has been divided into two parts. What are these two parts? The part on the left of I, because remember this is a sorted array, right? Everything in the array, it has been sorted. And I'm assuming that the sorting is done in the ascending order. So what happens is, the part on the left side of the array is sure to only have values which are smaller than this particular index, right? Because it is sorted. So whatever is there to the left, it has to be smaller, and whatever is there to the right has to be bigger. That is what is the definition of sorting. So the part on the left is sure to have only those values which are smaller than the value at index I, and similarly the part on the right is sure to have values which are larger than this index. So now if I compare my element to be searched with the element at index I can actually know that which part of the array my element may be present at. It may or may not be there, but I can say that at least one part of the array I don't really have to care about. Why? Because if my element is greater than the element at index I, it is sure that it cannot be on the left side of I. Similarly, if my element is less than the element at index I, it can surely not be at the right side of I. So now I only have to look at one of these two parts and not both. And if I do this repeatedly, right? So essentially, I'm just shrinking the size, shrinking the part of the array where I have to look. If I keep on shrinking it in each iteration, essentially I will end up with a single element part of the array where I can simply check whether my element is present or not. If it is present, I'll just say, yeah, found the element, or I can simply declare with confidence that this element is absent from this array. Okay. And if this I, right, which I said you can pick up randomly, if I basically say at each point, I'll just use the midpoint of the part of the array that I'm searching. Then this particular protocol, this particular algorithm is also known as binary search. So this is a very simple example. Let's just, it's the same array that we've been using till now. Let's just assume we have to search 9 in this array. 9 is here. So in the beginning, my whole of the array, is the whole part, the part of the array where the element can be found is essentially the whole array. Now what I do is, I just go to the midpoint, and this is 10. I check, okay, what is the relationship between 9 and 10. I realize that 9 is smaller than 10. So essentially, this part of my array, it becomes, it is of no more interest to me, because 9 can certainly not be in this part, because it is a sorted array, remember. Okay, and because 10 is greater than 9, it cannot be present in this part. It can only be present in this part. So I have already shrunk the part by less by half, right? This is what I have done, that in one comparison I can basically uh, leave half of the array, saying that okay, it cannot be present in this half. Okay, and now I only have two elements left. Now I'm not sure how to find the midpoint of these, of a two element array. So I can actually pick either one of them, to be honest. So I just pick let's just pick this one, so that I can elongate the process a little bit more. So let's just pick the 5, the index 0. I check 9 with 5 again. Now since 9 is greater than 5, because I know it is index 0, so there is nothing on the left of index 0, but just assume that if this was some other index and I had compared 9 with it, and I figured out that this value is less than 9, I can surely say, okay, so now 9 cannot be in this part, right? Because it cannot be, because 5 is already less than 9. This value cannot be here, it can only be on the right side. So now again, within these two elements I have discarded, saying everything on the left of 5 as well as 5 cannot have 9. So now I only have one element left. Probably I should have taken up a larger array. I just wanted to use the same array throughout the examples. So anyhow, so now I just have one element to check at. I check, okay, whether 9 equals 9, and yeah, it is. So, and this is where my element is. So this was a simple example of binary search. Go through your homework, there is a lot that is expected from you. Okay, and we'll discuss this on Monday. Okay, bye.